Hi, in this video, we're going to take a look at using logistic regression for supervised learning. All right, so logistic regression is a generalized linear model where our goal is to model the likelihood that an observation will be one of two different categories. Logistic regression is the OG model for modeling classification. Now, we're going to start out with just two levels, and that's all we're going to do in this particular video. But we can extend logistic regression to handle situations of like ordinal and multinomial situations also. If I need to do hypothesis testing, I am definitely going to be going to logistic regression or an extension of it in terms of trying to get like inference and understanding going on. For me, professionally, every time I do a classification model, I do logistic regression along the way. I also do a decision tree. Logistic regression, because of the coefficients and the interpretation of them, it's really a good way to go to get better understanding of what's going on. Also, logistic regression by far of the classification models is the best supported of all of them. So, this really is a good idea to get good at your logistic regression modeling. Now, when it comes to data prep, it doesn't matter what type of modeling I'm going to do. If I do good data prep for logistic regression, it's going to be good data prep for all types of models, whether that's like, stochastic gradient boosting or random forest or k nearest neighbors or naive Bayes or a neural network. Good data prep for logistic regression is good data prep, period. And logistic regression has more theoretical understanding to it than other models. And so this is a good baseline for us to understand what's going on when we make mistakes and we make poor decisions, or why certain things are a bad decision. Logistic regression helps clarify that. I would say linear regression is even better overall, but that's not a classification model. All right, so let's dig into it. So logistic regression absolutely is the most widely used method for modeling relationships. I actually spent my workday today doing logistic regression over and over and over, doing a little bit of parameter tuning and checking like benchmarking and stuff like that. While linear regression predicts a continuous outcome, logistic regression predicts the probability of an event occurring, specifically when there's two possible outcomes. So it could be an email comes in and we want a model to say, hey, this email is either spam or it's legit. Or maybe we're in the medical lane and there's a tumor and we want to decide, is it malignant or is it benign? Or we want to predict that a student will pass or fail on a final exam based on their behaviors going into the final. All right, so what we're going to be doing frequently is that we're not going to just take the classification of the predicted value. We're actually going to take the modeled probability value. And like at work, typically what we do is that we, talk to our stakeholders, we work through the process, and we say, all right, when we set a cutoff, and we consider what is the likelihood of according to the model, what's the likelihood of it going one way? What's the likelihood of it going the other way, according to the model? And then we consider what are the penalties if I make a mistake. So if I make, let's say I'm in the tumor situation, if I make a mistake, I say a benign tumor is malignant, there's going to be some problems. Or if I call a malignant tumor benign, there's also going to be problems. And when we do a classification like this, and for any type of classification, we have to consider what's going to happen when we make a mistake. One of the two is typically much worse than the other. Like here, calling a malignant tumor benign, making that mistake is much worse than the other way around, because the other way around, the doctor is going to keep looking at things and they're going to eventually conclude that things are okay. But if it's malignant and we make a mistake and we call it benign, there's going to be some problems because the patient's going to walk away. They've got malignant tumor in there, which is going to cause some problems. And so in our classification scheme, we always want to consider what's the impact of the mistake that we make. We will never be able, realistically, in real situations, we will never make a perfect model. And As such, we have to consider our cutoffs when we decide our classification based off of what is the penalty for making a mistake. All right, so let's go ahead and start digging in. So I'm going to load NumPy and pandas, and I'm using the mushroom data set. Now this is the prepared version of it. I prepared it in a previous video. This is the mushroom classification data set from Kaggle. At this point, that is a classic data set. And my goal is to identify the class where 1 is poisonous, 0 is edible. And on this particular data set, odor by far is the heavy hitter for this problem. Now, during the data prep video, I bend my categorical predictors into 3 different levels, low, moderate, and high probabilities of being poisonous. And I also went ahead and partitioned my data frame into train, validation, and test. And you can see that here. Also, I ordered my predictor variables from what appears to be individually the most informative to the least informative. I like to do this because it sets it up down the road as I'm doing my feature selection. It's very natural to figure out which ones I should leave if I put them in an order, beforehand. All right, so here is our list of predictor variables. I like to put all of my predictor variables in a list. Frequently at work, I'll have like a list numeric for numeric ones, list date for date variables, list ID for ID variables, list categorical for categorical, because that's how I'm going to handle them, each column differently depending on what they are. Frequently, it's by the data type determines how I handle them. And so here, all of our predictor variables are categorical. So I just have list predictors. That's it. And I'm going to set up what my my design matrix is, the X. And so here I'm just taking my data frame of the predictor variables. Here is Y is my target for this, which is just the class of poisonous or edible. And now here, X train, I'm just limiting things to the training data set. Y train, I'm limiting the target variable to the training data set. And let's go ahead and take a look. Now this is of the entire data set, not just training. And we can just see that, there's a, just below 50% are poisonous. Now, a very natural question that could come up is like, well, why don't you just use linear regression instead of binary, logistic regression? Well, there's several reasons for that. I mean, the punchline is we're not going to get the full oomph of our model, most impact possible if we use linear regression. So, if I'm talking about probabilities from 0 to 1, those are continuous. Linear regression gives me continuous values, but there's some good reasons why we're not going to go to linear regression. First and foremost, we're going to get predicted values outside of 0 and 1. So if I was to attempt regular old linear regression for probabilities, I would invariably end up getting like a negative probability or something greater than 1. Well, that wouldn't make sense. I could, round it down, round it up, I could, but it's just better to have a natural system. Also, when I go through and do my analysis, if I try linear regression, well, linear regression makes the assumption of Gaussian residuals. That's definitely not going to be the case in this situation because my observed values are 0 and 1. So it just can't handle that way. Also, there's a nonlinearity aspect to predicted probabilities. All right, so if you think about linear regression, if I increase a predictor variable by a certain amount, on average, I expect my target variable to increase or decrease, according to the coefficients. All right, well, if I try it with probabilities, well, let's say I increase a predictor variable when the probability was 0.99. Well, a little bit of increase in the probability, it's over 1. Also, I could easily go below 0. And if I have a probability close to 0, then I start tinkering with the values of the probabilities. This is more applicable to the situation where I'm using my model for like control of a system, like in an assembly line or something like that. Also, linear regression makes several assumptions that we just absolutely don't have. First of all, linearity. There is a linear relationship between the predictors and outcome. It can't be linear because it'll overshoot 1 and overshoot 0. Independence between the observations, all right, well, that one's fine. Homoscedasticity, equal variance of residuals, is not going to be the case. If you look at if I take the probabilities for binomial and look at the variance of a binomial distribution, it's not constant. It changes with the probabilities. And so here, I'm not going to have constant variance off of this. Also, I can't have normally distributed residuals because of how I've got zeros and ones observed. And so, it's just going to cause problems if I try to do this. Now, could I do it? Yes. If someone put a gun to my head and forced me to do it, yeah, I'd go ahead and do it. Um, you know, the only reason I could see you legitimately using it is to get estimates of coefficients to, if I was in like a really, 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 really big data problem and wanted to estimate the coefficients beforehand to get convergence faster, I could see using it, but really don't do it. Just don't do it. All right, so now for data prep for logistic regression really mirrors the data prep for linear regression. And remember, linear regression, good data prep for linear regression is good data prep for all model structures. So when you're going through and you're building your models, that's a good mindset to have, that I'm going to make the best data set I can for linear regression, and then I'm going to use the same data across different model structures as I explore different models for what's going on. And so logistic regression cannot tolerate any missing values in an observation. So if a row has one or more missing values in the predictors, the logistic regression has to kick the whole thing out. That's going to be a problem. All right, so if I'm in the situation where I have missing values, either I need to omit records with missing values. That's the classic way to go about it. But when I've got a lot of predictor variables, and that can end up just like whittling down my data way too much. So a lot of times in machine learning predictive analytics, we'll go ahead and do imputation. So like my boss likes univariate imputation because he likes to know that when I impute, he likes to know the exact value that's going in there. He doesn't want any ambiguity in it. He likes to really, really know what's going on. I disagree with him. I like other techniques, such as tree-based or k-nearest neighbors imputation, but whatever. It's all good. Now, outliers, just like in linear regression, logistic regression is going to have problems with outliers. If I look at the hat matrix, the whole concept of leverage in hat matrix actually doesn't even need to have linear regression going. It's applicable to other types of model structures. And we can use leverage as a measurement of, hey, maybe I want to treat this guy like an outlier. What's going to happen if I have outliers in my data set is that outlier is going to pull the model away from central tendency of the data towards itself. And so we don't want that. We want it to, we want the model to look like the data as much as possible. And so my options when I have outliers, I'm going to fix this real quick. This is one thing that's nice about Jupyter notebooks instead of, oh, it didn't do it. There we go. My options for outliers is first and foremost, just leave them alone, but note that they're there. That might be where I'm at. So like if I was going to be under legal scrutiny, because if I start tinkering with the data, maybe a lawyer or a rival will say, hey, you messed with your data. That's not legit data. You're falsifying. So I might just leave it alone, just realize it's there. We can remove outliers, or we can replace outliers with less extreme values. That's my personal preference. Do whatever your stakeholders want you to do. Now, feature scaling. Typically, I prefer to subtract by the mean, divide by the standard deviation. That will give my predictor variables a column mean of 0, standard deviation of 1. Other people like to, rescale things to like 0, 1, something like that, -1 to 1. for the type of data I work with, typically we don't know what the maximum and minimum possible value is. And so here, since I don't know the upper and lower bounds, I like subtract mean divided by standard deviation. You know, when I do this, rescaling with linear regression or logistic regression will not improve or degrade your model performance. So rescaling my predictor variables, what it'll do, it'll set it up so that I can use variable importance as the magnitude of the coefficients. And so now it's important. I have to rescale my predictor variables first. If I rescale my predictor variables, then I can use coefficient magnitudes as their absolute value to represent variable importance. If I don't rescale for variable importance, I need to use a t-test statistic off of it, which scikit-learn really does not support. There are ways to get it, but really I need to be using R or stat models for that, if that's what's important to me. Now, the coefficients are more difficult to interpret if I scale them. Why is that? Because it's not as clear of a relationship. I have to find the rescaling, function, and then, connect that back using a little bit of mathematics to the coefficients to figure out, what was the interpretation. Either way, you're not going to change the actual predictive performance of your model. Now, also, just like linear regression, logistic regression cannot use categorical or ordinal predictor variables. It has to be numbers only. And now, notice that I'm saying no ordinal predictors. So if I had high, medium, low, first place, second place, third place, those aren't numbers. And as such, I can't have first place, second place, third place as predictor variables. Now, if I was to convert that over the numbers, 1, 2, 3, maybe a lot of statisticians will say don't do that, but that's for a different video. So in scikit-learn, every single model has to have only numeric predictor variables. And so I'll have to do dummy variable encoding. Now, when we're fitting the model, the classic way to fit the model is to use maximum likelihood estimation. All right, so what this does is that this takes the observed data, the independent variable values and the dependent variable values, and figures out the coefficients and intercept that will give the maximum probability under the hypothesized probability distribution. Now, something that we need to make a distinction with is that if I'm talking about a probability, I'm talking about an event that is going to happen in the future or may have occurred in the future. And so with a probability, this is an event that hasn't happened yet. A likelihoods are measured on the same scale as probability, but they've already happened, or maybe they haven't. Likelihood is a more flexible word. When we say probability, we refer to an event that hasn't happened yet. So for example, let's say I flip a coin and I hide it under my hand. I don't know what it is. Now, the probability of heads is 0 or 1. It is or it isn't. 0 or 1. 0 probability if it's tails, 1 probability if it's heads. The probability of heads is 0 or 1 because it happened or it didn't. Now the likelihood is 1/2. And so when I lift my hand up, now I know what it is. There's no ambiguity, no likelihood left at all because we know exactly what happened. And so, when we do maximum likelihood estimation, best fit means that we're going to get the maximum likelihood possible using the classic likelihood function, where in that situation, we treat the coefficients as the variables and we treat the observed data as constants. And then we drop it into the probability distribution function that's multivariate. And then, we do like calculus. Well, actually, we're not going to do calculus. We're going to have an iterative algorithm do it for us. Hypothetically, if we were super, super good at calculus, we could sit down and try to work it out, pencil and paper, and approximate it There is not a closed formula for logistic regression, maximum likelihood, but potentially we could get a pretty close approximation. We could get it to converge it by hand if we had to, but we're not going to do that. We're going to just let the numerical algorithm run. All right, so now when we estimate the conditional expected value, remember that we're doing a generalized linear model. The generalized linear model is that I'm going to have my intercept and coefficients times predictors on the right, and on the left, I have the log odds. All right, so the expected value, remember the expected value is the probability when I'm dealing with a Bernoulli random variable. So the expected value is the probability of success, the probability of 1. So I have the probability here. Here's the probability of it not occurring. This is the odds, and I'm taking the log odds on the left. All right, well, if I go in to this formula here and replace expected value with the probability here, and then I do a little bit of college algebra, I can see that the probability that y is equal to 1 is equal to this fraction here. Okay, and so if I look at this for a moment, look at what's going on here. Okay, what would happen if what's highlighted, all the betas and all the x's, after I do the multiplication, I add them all together, I get something super, super, super big. Let's pretend that's infinity. Let's think about the limit as it goes to infinity, as a whole summation there goes to infinity. All right, then this is infinite. I have e to something approaching infinity, which is going to be infinity. Then I have 1 plus something going off to infinity. Okay, well, if I do a little bit of calculus, divide by the e thing, I'll notice that the limit of the whole thing is going to be going to 1. So for a large value in the exponent of e, if the exponent is very, very, very large, then the probability is close to 1. Now let's go in the opposite direction. Think of the exponent being super, super big and negative after I do the intercepts plus coefficients times predictors, add it all up. I end up getting a very, very, very large negative value. Well, then e is going to be very close to 0. The numerator is going to be close to 0. The denominator is close to 1. 0 divided by 1 is 0. So the probabilities will be close to 0 if the exponent is large and negative. Okay? So now let's talk about estimating the parameters. So classic logistic regression, we have no penalty at all. That's the maximum likelihood estimate, and we just run it. Well, times have changed, and we've got more modern techniques. So what we can do, we can try ridge, lasso, or elastic net to help protect us from overfitting in our model. What these will do, these will penalize our model for having a larger coefficient, either the L2 or L1 or a combination of the two on the coefficients. And so if I want that, I just put penalty equals L2 if I want ridge, penalty equals L1 if I want lasso, and penalty equals elastic net if I want to use both of them. Now, one thing that you need to know about if you're going to be using scikit-learn is that the default is L2. Or L2, this means that when you sit down and you run the model, the default setting, if I don't tinker with anything, I'm not getting maximum likelihood estimation. Maximum likelihood estimation is by far the most established, most well understood, most accepted way to estimate the parameters. And so if I didn't check the help documentation, I wouldn't know that I wasn't actually doing maximum likelihood estimation, which could be a problem down the road when people start scrutinizing my model. Now, lasso will go ahead and perform feature selection for us. What it will do is it will shrink coefficients down to 0, which we interpret as that predictor variable gets kicked out. Ridge will always, up to rounding, will always have a non-zero coefficient for all meaningful columns. All right, well, ridge, if I'm in a situation where I need to keep all the predictor variables, even though I'm worried about overfitting, even though I'm worried about collinearity, ridge is a good choice because it'll shrink it down. Lasso is good for doing feature selection. Now, feature selection and ridge and elastic net are not a substitute for good feature selection. We need to do our, good solid data prep. We need to do good solid, feature engineering, and we need to do good solid feature selection. If I don't do good feature selection, I just throw everything in, ridge and lasso will make it a less bad situation, but I'm still in a bad position. Do your feature selection. All right, so now we need to talk about the solver. So the solver is just the parameter by how scikit-learn Python is going to actually execute to figure out what the coefficients are going to be. We have several choices. We have LBFGS, which is the default. We have liblinear, which is a good choice for small data sets. We have Newton CG and Newton Koleski. Newton Koleski is a good choice when our sample size is much bigger than our features, especially when we have one hot encoding going on, our dummy variables. I copied and pasted this from the help documentation. Liblinear is good when we do one versus the rest schemes for multinomial. And for multi-class problems, only Newton CG, SAG, and Saga and LBFGS handle multinomial loss. All right, so this is just here to help you, judge which one to go with. Part of my day today, I was benchmarking logistic regression models because I know that going forward, I'm going to be going through. I'm going to be, building a model, check it, build a model, check it, build a model, check it through this, back and forth process. And I'm going to pick the solver that gives me the result fastest, so that way I don't spend a lot of time waiting for the computer to compute. The top four were pretty quick for what I was working on. SAG and Saga both were pretty slow on my personal data set comparatively. Now you'll notice that only Saga has elastic net. So if I want to use elastic net, I'm stuck with Saga no matter what. I recommend that you benchmark your models and check to see which ones will be fastest for your size of data, and which will be a combination of number of predictors and number of rows. And SOG and Saga, they give fast convergence only when our predictor variables are on the same scale. And so we can use the pre-processing functions to put things on the same scale. Okay, so let's go ahead and start building up the model. So I'm going to have different penalty. So I've got maximum likelihood estimate, L2 penalty, L1, and then combination of L1, L2. Here, I'm just creating a list of the models before they're fit. I'm creating a list of the fitted models on the training data. And so now I've got a list of my fitted models, and I can use these very nicely. I like to keep my objects that are similar to each other that will be operated on in the same manner in a list, all nice and neat. I find this is a better way to do your statistical programming. Okay, now, something about scikit-learn. Scikit-learn really does not give us a lot of flexibility for our linkage. That really we only get to use log link or the logit link for logistic regression. And so that's really not optimal. Some fields of science and economics and social sciences, they have their preferences. I've encountered researchers that really like probit. Well, scikit-learn isn't supporting probit, at least as far as I know. And so if I want to do probit, I need to do stat models, or I need to go over to R. Either way. But it works out that the logit link is pretty flexible. So if I made the wrong call and I use logit when I should have used a different linkage, I'm usually okay. It's usually not a big loss. It's a pretty flexible one. The exception to that would be like a C log for like survival analysis, because that's an asymmetric linkage. But the rest of them are symmetric that I know. The rest of them I know of, I can think of in R, are symmetric. And so the S-shaped curve for logit tends to pick up what we want. The S-shaped curve is a sigmoid curve, and it's symmetric about that's odd symmetry. I could about 1/2. If I put my finger at the point that for probability of 1/2, I could spin it 180, I get exactly the same curve. All right, so now when we talk about interpreting our model, we've got log it of the probability is equal to the log odds. And this is our relationship. Now for maximum likelihood estimation, how we're going to fit our coefficients is that I'm going to take that likelihood function I showed you a little bit ago, and I'm going to pick the parameter values that maximize that likelihood. And you notice I've got beta hats on here. Now for interpreting the coefficients, the intercept is going to work in an indirect manner to shift our curve left to right. It's going to be an S-shaped curve, and it's going to get shifted left and right by the intercept. How to see this? Now, this is something I've never seen written down, but if you think about college algebra, it's pretty obvious. So recall from college algebra that f of x plus h, the h is on the inside of the parenthesis, is a horizontal translation of f by negative h. Notice it's in the opposite direction. I've got plus h, opposite direction h, okay? And so if I think about that, if I took e to the beta x, let's say I take e to the beta x, I replace x with x plus h, I see now I get this. Well, the intercept term right here this is going to be my intercept, this beta 1 times h. And so effectively, what's going on, this h is a translation of a S-shaped curve. And here I get the intercept. Now you'll notice that's not a direct relationship. It depends on what is the slope of the predictor variable that is getting translated. And so here, this is for this purpose, this is my baseline curve. So I have a slope of beta 1 and an intercept of 0. And so now when I do the translation, I still have the same slope, but my intercept is beta 1 times h. Okay, so that's how we interpret our intercept. And so we just know that it shifts it left and right, and there's a coefficient aspect to it. Usually we don't get too deep into this. Now the continuous predictors, now this is a little bit juicier. All right, so what I'm going to do to see what is the impact of a coefficient, increasing a predictor variable, up or down. What I'm going to do, I'm going to consider the probability when x is the value it is, and when x is x plus h. So here I'm doing that translation thing. All right, so now here I've only got one predictor variable to make things as simple as possible. And I've got the log of this. You'll notice I've got the x plus h in here. It's a translation. Here I got regular old x. Now I've got log on the left, and I've got just straight add-ins and on the right hand side. So let's go ahead and subtract this equation from this one. Okay, so then I've got log minus log equal to all this. Well, this is just going to simplify. The beta zeros cancel with each other. The beta 1 x's cancel with each other. And on the right hand side, I'm beta 1 h. Now, remember from college algebra, I subtract logarithms, it gets converted to division. So now I have the log of the ratio of the odds. Okay, well, let's go ahead and simplify this if we can. Now this equation is perfectly legit for our interpretation, depending on what I'm working on. But let's go ahead and take this a little bit further, because that might be a little bit easier to interpret for what we're doing. Okay, let's take e of both sides. So now I've got the ratio of the odds is equal to e to the beta 1h. Now I'm going to multiply both sides by the fraction on the bottom of the big fraction. And so now I can see that the odds after translation is equal to the original odds times this e business. And that gives us our interpretation. Now, the interpretation is a little bit clunky. It's not as nice and clean as regular old linear regression, but this is by far the most informative interpretation we're possibly going to get. Now, for categorical predictor variables, we take the continuous predictor variable interpretation, but we have either 0, 1, or +1, -1 for our values. All right. And so now if I'm working in scikit-learn and I want to get the intercept, all I got to do is use dot intercept on my model. If I want to get the coefficients, it's dot coef underscore. Notice that I'm rounding the values just to make it a little bit easier to interpret. And so here, this is my maximum likelihood coefficients. This is my L2 penalty coefficients. This is my L1 penalty coefficients. And over here, this is my elastic net coefficients. And so I can go through and do the interpretation for any of these for whichever model I would choose. You'll notice that with lasso, we actually get down to 0. And in this situation, we interpret that as this is getting excluded from the model. If I look at ridge, notice that that 0 is a negative sign. All right, so what's happening is that ridge doesn't actually get truly to 0. It's actually a non-zero value, but up to rounding, it looks like 0. Now, to make predictions, we have two different ways. Just like in other functions in scikit-learn, we can either use predict. Now, this will give us the classification, either 0 or 1, or I can get the probability using predict proba. Now, when we do this, I'm going to end up getting columns for each level of the target variable. Here, we're doing regular old binary logistic regression, so there's two levels. So I'm going to have two columns, column 0 and column 1. And you'll notice that this part here is for just saying, hey, I just want column 1. I just want to know the likelihood of poisonous, because if I know the likelihood of poisonous, I know the likelihood of edible right out the gate. And so here, and notice I'm keeping everything really nice and clean together in my list. I don't have a bunch of things floating around. I don't have anything in any individual object floating off by itself. Each model, each fit, each prediction is in a nice container. Now we also want to do model validation. There's a couple of ways to go about this. It depends on your project. Most of the time, we're not going to just accept default cutoffs for classification. Most of the time, we're going to consider the penalty of making a mistake. AUC does a good job of evaluating as a whole. When I start changing the levers, changing the values of the cutoffs, how good is my model? Now, this isn't directly connected to, there's a gap between AUC and accuracy. There's a gap between AUC and sensitivity, AUC and specificity. They're all related to each other, but different models can have one lower than the other and the other would be higher. It doesn't have to perfectly correspond. Generally speaking, if I have a really, really good AUC or a really, really low AUC, the other statistics are going to be good or bad corresponding. And so here I'm just going to go in, I'm going to get my AUC for each of these. Now I've got train, validation, and test. Now here the model looks fabulous because odor is so powerful as a predictor variable. Here is for maximum likelihood estimation, the first three, the second three, with the 1 is for ridge, then for lasso, and then for elastic net. Because I have such a good solid predictor variable, this is an easy modeling case. I'm absolutely nailing it with this. But you'll notice that these aren't quite perfect models. Don't ever expect a model to be perfect. There will be times that it's going to make a mistake. All right, so now let's go ahead and plot the ROC curve. The ROC curve is a visualization of how things will go as I change the cutoffs for saying poisonous or edible. And with this good of a model, it's really meaningless. The ROC curve. So if I was just to do random guessing and I set a cutoff, between 0 and 1, do uniform random number generation, and I set a cutoff based off of the random values without even looking at my data, this line here, the y equals x line, would be our performance in terms of true positive and false positive rates. Now, the model is, if I take every single possible cutoff for declaring poisonous or edible, there's going to be a curve that fits here, and it's a steel blue curve. and this is like a nearly perfect model. Um, and so we can see that since it's so good, this is going all the way up here and over here. It's forming like a square. This is maximum area under the curve. And typically we're gonna have something that looks kind of like a bow above the y equals x line. And the model is so strong because of the odor predictor variable. It's meaning us to look at that. Now, all right, so now for variable importance, if I did my rescaling, variable importance will be the magnitude of the predictor of the coefficients. If I want to go through and reduce my model to have fewer predictor variables, I want to remove one at a time, low important variance, very low variable importance variables first, one at a time. I remove a predictor variable, refit, remove a predictor variable, refit, do this over and over. Now, the interpretation of magnitude as variable importance really only applies if I rescaled the values. If I didn't rescale, then I can't trust it. I need to go to like a t-test statistic, which scikit-learn really does not support. You can get it, you can force it through. Realistically, if I wanted to use a t-test, I would go and use stat models or use R. All right, that's all I got for you. What I want you to do for homework, I want you to rescale your predictor variables so that they're on the same scale. I want you to build models with all four penalties, that is none for maximum likelihood estimation, L2 penalty for ridge, L1 penalty for lasso, elastic net, and then I want you to visualize the coefficients using a bar plot. Tell me what you see is different between them. That's all I've got for you. Life is short. Do math.